let me introduce you a little bit background of logistic equation. It was discovered and imposed on biology as a simple model of population self-regulation in the early 20th century by American biologist Raymond Pearl and his disciples. It was proposed in the first half of the 19th century by Belgian mathematician Pierre Francois Ploners in 1838 as a potential solution to the dilemma of material exponential growth. Since its invention, it has been applied in many domains of study including ecology, chemistry, population dynamics, and many more. There are three main objectives. First, to compare results between manual solution and manual and computer-aided solution. Second, to describe the graph pattern of growth production. And lastly, to know the application and related the logistic equation in biotechnology.
Warehouse developed the logistic equation to describe the biological population self-limiting growth. The logistic equation model depicts population growth within a carrying capacity. It is assumed that the rate of growth reduces linearly with size until the carrying capacity is zero. The logistic equation, in which the rate of reproduction is proportional to both the current population and the amount of available resources, is widely used to estimate the population expansion. The mathematical representation of that is included in the slide.
Assalamualaikum, I'm Nabila. As for my part, I'll be explaining a few applications of the logistic equations in biology and biotechnology based on our research. Firstly, it is applied to model the progression of tumors. The logistic differential equation is used to model the progression of tumors in medicine, where the logistic curve is used. It is a crucial component because it will aid in predicting the tumor's course and optimizing treatment regimens. Secondly, to interpret the COVID-19 epidemic data, in various countries, the generalized logistic equation is used to interpret COVID-19 pandemic data. The growth rate and expected number of infected people as well as the exponent indexes in the generalized logistic equations are determined. Thirdly, to analyze the dynamics of cell growth and protein production in mammalian cell fat batch systems, the logistic equations are accurately represented the experimental data in both cases, and the ensuing specific growth rate and protein productivity profiles provided valuable insights into the process dynamics. Calculations of the growth of bioproducts, which are bacterial biomass as dry weight, cell formation, lactic acid production, and acetic acid production for sample 1 and sample 2 were made using the logistic equations and time, with the symbol T will be substituted by 1 until 20 in the equation. And these are the logistic equations for sample 1 of our group, which is skin of Atlantic host mackerel. While these are the logistic equations for sample 2 of our group, which is head of Atlantic host mackerel.
For results, the first table, table 1, is the result for skin Atlantic host mackerel using the manual approach. Table 2 is the result for head Atlantic host mackerel using the manual approach. Now, table 3 is the result for skin Atlantic host mackerel but using the computer-aided approach. Now, table 4, our last table for this slide, is the result for head Atlantic host mackerel but using the computer-aided approach. And after we compare, both the computer-aided and manual approach yield the same answer. For this part, it shows the graph that was made using table 3 and table 4. And the graph can be disseminated into 3 parts, which is the lag phase, log phase, and stationary phase. The lag phase is characterized by the extremely low metabolite production due to small number of bacteria present, and the log phase is characterized by the rapid increase in metabolite production over time. And lastly, the stationary phase, the metabolites production is leveling off because it has reached its carrying capacity.
The increasing pattern of bioproduction's growth for both skin and head of horse mackerel have resulted in a sigmoid growth curve. There are 3 phases of growth that can be observed from the graph, which are lag, logarithm, and stationary. Based on the data, Lactobacillus brevis produce more biomass cells and lactic acid in the skin of horse mackerel. Meanwhile, in the head of horse mackerel fish, yields a high growth for acetic acid compared to the skin. To summarize, logistic equation is a very good approach in monitoring the bioproducts yielded by the skin and head of the horse Atlantic mackerel. Although the value produced by logistic functions are very close to the estimated values based on prediction data, computer-aided method is more accurate as the results given is up until 18 decimal place